Hi everyone. So this is our third look at electricity and magnetism, mainly just electricity so far. And we're going to talk about how being an electron on the move is hard sometimes. Sometimes you've got choices to make, and sometimes, no matter how hard you try, it just seems difficult to get along in the world. So, looking at different types of circuit in a basic sense, we've hinted before that there are at least two different types, and that is series and parallel. But what do we mean when we say that one type of circuit is a series circuit and another is a parallel circuit? Well, in the most basic terms, a series circuit follows just one electrical path, whereas a parallel circuit has two or more different possible paths for the electricity to go down. So in many ways, the series circuit is the most simple type of circuit, and the parallel circuit is building on to that. So we're going to look at a series circuit first, and here we have a simple series circuit. So up in the top left of the circuit, you can see the battery that is represented by two small cell icons. And then going clockwise around the circuit, we come to two bulbs. And then there is a switch, which is open. And then finally, a resistor, which is the name for that little zigzaggy line component. So, if we close the switch and we see the electricity going around the circuit, we can see that it follows just one path all the way around the circuit, and it gets to every part of the circuit. So, that is a very simple series circuit. So let's think about voltage in a series circuit. Now, remembering back, we have to measure voltage across a component. So at each component, there will be a potential difference across that component. And we want to think about how that will relate to the total potential difference, which is going to be VT, the total voltage. And that's the potential difference purely across the battery. So if you have a quick think about that, the voltage VT is going to be the sum of the potential differences across each component. That's not a terribly difficult leap to make. It's going to be adding up all the voltage differences to make one final total difference. So in other words, VT equals V1 plus V2 plus V3, where those voltages are across each component in the circuit. So we move on to the parallel circuit, which has multiple electrical paths. So these paths run electrically parallel, but it is often convenient to draw them parallel on a circuit diagram too. It helps keep things nice and organized. So the amount of electricity that passes down each path depends on the components that are along that path, and this is going to make parallel circuits much more complex than series circuits. So this is a parallel circuit, and you can see the current flowing along both paths, the middle one and the outside one, and it cannot backtrack, so it has to flow through both in order to get to every part of the circuit. So what do you think the voltage is going to do in this case? So similar to the series circuit, we're going to be adding up some components to get the voltage that is across each path. So there we can see that V1 is going to be the potential difference across the bulb, and then add that to the potential difference across the resistor, whereas V2 is just going to be the potential difference across the bulb. But where this gets a little different is that because the potential difference across the whole circuit is going to be the same, that means that the potential difference across all of the possible different paths must be the same. So the electrons going down both paths still have to lose the same amount of electric potential energy by the time they get to the end of the path. So if the voltages are the same along both paths, that means that VT equals V1 equals V2. The total potential difference across the entire circuit is the same as the potential difference along every individual path. So far we have seen that along a path, the potential difference is the sum of the potential differences across each component on that path. Along multiple parallel paths, the potential difference across each path is the same. So with those two things in mind, we're going to look now again at the water analogy and see how this relates to a new property. And that property is resistance. So, as we have said, electrons pass through conductors quite easily, but other conditions can make it harder for electrons to pass through any material, conductor or insulator. There's always something resisting the flow of electrons. What do we call this property? Well, you might be able to guess. So if we think about the water wheel that we saw in the last video, when water goes through that wheel, it doesn't just flow smoothly like it was doing before. It has to force its way through, and this slows down its progress. Resistance in electrical circuits is quite similar. So let's look at the water analogy here in a bit more detail. So here is our parallel circuit, and if we just map over a similar system in terms of water, you can see that that middle path now is much narrower. The resistor at the bottom is represented by a very narrow bit of pipe, so when the water flows through and comes out of the bottom of the pipe, the water coming out of the middle path is reduced. There is less water coming out per second. The wider path is still passing out a lot of water, and so what is the difference between these two? The water going in at the top comes out at the bottom, and it has lost a certain amount of gravitational potential energy because of its change in height. And by using a pump, a battery, in the electrical case, we can pump that water back up to the top. We put in this energy from the pump. However, the water at the bottom of the system has always lost the same amount of gravitational potential energy, no matter which path it came down. It always gets to the same height at the bottom. So this shows us why the voltage is the same along all paths in a parallel circuit. It's because no matter which path it goes along, by the end of the circuit, it has lost the same amount of electrical potential energy. So what exactly is reduced? Well, if we think about less water coming out per second, that is the flow. So we can see that the voltage across both paths is the same amount of potential energy is lost, but the amount coming out per second is the flow, that is the current that is reduced. So all electrical components have some resistance, but in things like wires, for example, we take it as being next to zero. However, here are two examples that we actually saw in our circuit. There is a light bulb on the right, even though that is quite an old-fashioned light bulb now. On the left, we can see a resistor, which is a component that is specially made to increase the resistance of a path in a circuit. So resistance, if we're going to define it, is an obstacle to electrical current. It's a measure of how difficult it is for current to get through the path. So if the path is very narrow or very long, that is one way that it can make it difficult for electrons to pass through. And if we think about the old-fashioned light bulb, you can see perhaps why it was so difficult for electricity to get through that filament. And it's very long and very narrow, and so it has a much higher resistance than a normal wire, and this means a lot of electrical energy is going to be burned there, and that is given off as heat and light. So you might have seen that the filament was a coil before, but did you see that it was a coil within a coil, made of tungsten, which has a very, very high melting point, because metals with a lower melting point would just have burnt out. And you may remember that these light bulbs did sometimes burn out just on their own. So now we've seen how the relationship between voltage, current, and resistance works, we can put it in mathematical terms, the first major equation of electrical science, and that is Ohm's law, discovered by this gentleman, George Ohm. And he discovered the proportional link between the voltage across a conductor and the amount of current going through it. And this link was proportional to, you guessed it, the resistance of the component. And that gives us a lovely little triangle equation, which is more commonly stated as V equals IR. V equals voltage in volts. I equals current in amperes, of course, and resistance is measured in ohms, and that's given a rather strange symbol. It's actually the Greek alphabet letter omega. It's a capital omega, and that is the unit that is given for ohms. Of course, if we used an O, that would be incredibly confusing, so that's probably why we use the omega symbol. Works quite well with his name though, right? Ohms, omega. So that's where we'll leave it for this video. We've introduced parallel and series circuits, and we've introduced the idea of resistance, and we've come to our first major equation, Ohm's law. So in the next video, we'll look a little bit more about how that works in some of the circuits we've talked about.